So good afternoon, everyone. My name is Condy, and today I'm going to present you my study evaluating large language models' ability to play board games. First, starting with the introduction. So a general overview to my presentation. The presentation will be divided into three parts. The first part is the background information. Second part is experimental design and results, where I'll explain the actual study that I did. The last one is the conclusion of my experiments and the future implications of my study. First, the background information. As a reminder, my topic for this study is evaluating a large language model's ability to play board games. So I first looked at some previous studies on AIs and machine learning board games. The early examples of research in this direction include Deep Blue, which is a AI model that played chess in the 1990s. It defeated the world champion back then. And since it was the game of chess, which didn't include so much branches and so much calculations, it was much easier than the game for excuse me, I don't think I heard it correctly. Can you repeat your question?
No, I think someone didn't mute herself. It's okay. I think she muted herself. Now you can keep going.
Okay. Oh, it's fine. Thank you. So in recent decades, since the computing technology and computing power have increased exponentially, we have expanded similar similar approaches to complex games like Go. So in the last decade, DeepMind invented a new machine learning model that can play Go, and it performs really well. It is capable of defeating the Go champion in the world. This demonstrates the growth in AI's computing power and ability throughout the decades. And in even more recent years, they're having large language models. And very importantly, ChatGPT was introduced in 2022, and they have shown similar capabilities in performing logical reasoning skills, although there haven't been any previous studies done on their ability to play board games. That's why today I would like to present mine. There have been previous efforts to increase the capabilities of existing large language models. For example, last year there was a study trying to increase the language model's ability to store information in the long term. I linked the study in my research paper. The approach is called MemPrompt. You can read about it later if you're interested. And then the more important part of the effort to increase the capability of models is devising good prompting strategies. There have been many studies that are done on prompting strategies, and notably, the standard prompting strategy that we use without any consideration is zero-shot prompting, which means that we just ask a question without any additional information given. And then few-shot prompting, the few in few-shot prompting represents however many examples that you give to the questions. So for example, if it's one-shot prompting and you ask the model, what is the fruit? Then you'll have to attach an example to the question. So uh, one example would be, what is fruit? An example is banana, and then you input the prompt into the model, and then the model can give a response to your question. And two-shot just gives two examples. So what is a fruit? Examples will be bananas and apples, and then the models are shown to perform better as you increase the number of examples you give to the model. And then there's repeated prompting, which means you give real-time feedback to the language model. So if the model gives you the wrong response, then you tell the model that it gave the wrong response and you ask it to fix it. And then there's more complex prompting strategies like chain of thought prompting and tree of thought prompting. Chain of thought just basically asks a model to think about the question step by step and ask it to output all of its thinking progress line by line, and it allows the model to more clearly follow a thinking pattern and logically output its response. So as for the actual experimental design, I selected 3 games based on their complexity, relevance, and strategic depth. The first one is Tic Tac Toe, and the second one is Connect Four, and the last one is Chess, in increasing difficulty levels. I figured that by selecting these 3 board games, I'll be able to gain a comprehensive understanding of large language models' ability to performing games of varying difficulty. I divided the problem into 2 parts. The first one is board state interpretation, and the second one is strategic reasoning. I will explain these 2 separate parts in more details in the next few slides. But by dividing the problem into 2 parts, I can evaluate its ability into 2 different criteria. So I thought it would be better for a comprehensive knowledge of its ability. Obviously, without interpreting the board state correctly, the model will not be able to perform very well because it doesn't even know what the board state is like. And without strategic reasoning, the model will not be able to make logical decisions and good moves. So the first subsection of the board state interpretation part of the experiment is stateless interaction. Stateless interactions refers to the inability of large language models to operate at the same time with remembering the previous conversation's details, because nowadays the language models rely on tokenization of information. So when the information is really complex, its ability to recall previous tokens and informations decrease exponentially. So I designed an experiment to demonstrate that the models cannot indeed recollect the previous board state interactions. The experiment is I selected board games to play with the large language model. And in this case, I selected GPT-4 because I thought it would be the most representative of modern large language models. And then I monitor if the model is able to keep track of the board state throughout the game. The result of my experiments is in Tic Tac Toe, which is the simplest of the games, the board remains consistent and correct throughout, meaning that the large language model is able to follow the progress of the game correctly. And then in Connect Four and Chess, which are more complex than Tic Tac Toe, the computer is unable to remember the moves correctly and represent it to the user. So this is generally in line with our hypothesis that as the game becomes more complex, the ability of the models to remember the board state correctly decreases. To illustrate this example, I'm now going to show a live conversation with GPT-4 to show that it is indeed not capable of remembering the information directly in more complex games. So, for example, if I ask GPT-4 to play a tic-tac-toe game with me and ask it to represent the board state with ASCII code, meaning that it'll output it in a graphic way. As you can see, although it lost the game, it is able to represent the board correctly throughout. But if I switch the game to a more complex one like Connect 4, you can see that it's not capable of understanding the game's mechanism. The piece that it played did not drop to the bottom row, so it cannot represent the board correctly, and it's just not capable of playing the game correctly. and it shows this deficiency in playing board games. Now continuing with our slides, the second part of board state interpretation, I designed an experiment experimenting the complexity and GPT's ability to encode and decode information correctly. So in this experiment, I supply a board state, whether it's in Connect 4, Tic Tac Toe, or chess, using the standard representation of board state. In the case of Connect 4 and Tic Tac Toe, I use ASCII, and then in the case of chess, I use FEN, which represent the board state in a line of code. And then I make an additional move to the model, and then I ask the model to output a new board. If it's able to output the correct board, then it means that it's able to correctly decode the user's information and move, and also able to accurately encode the information back to the user. If it's unable to do so, then it means that its encoding and decoding capability is not good. And the result of this experiment is that among the 150 positions that I enter to the model, in this case, I use API because it is more efficient to when I have a large amount of trials I need to do. The ending result is 9.3% accuracy, which is shockingly low because if it's only able to comprehend 9.3% of the information that the user inputs, then it means it is definitely not capable of performing well in complex games. So this, in conclusion, these two sub-experiments conclude that GPT and modern large language models in general are unable to interpret the board state correctly yet. And then the second part of our study, which is the more important part, is the GPT and large language models' strategic reasoning skills. I also divided this experiment into two parts. The first one is sequential and parallel processing, and the second one is prompting strategy. Modern language models, they process information and think in a sequential way, meaning that they only have one line of thinking. They just think in a straight line. They follow one line of logic. While as humans, we consider multiple choices and options at the same time. Models don't have the same ability to do so. So this might be affecting language models' ability to make the best moves because they can only consider one choice at a time, meaning that their search tree might not be wide enough to consider all the good candidates move. And then to illustrate this point, we designed an experiment in two parts. The first one is we try to after the experiments and after we get the results in the first experiments, we understood that the models aren't able to play the games correctly. So in the second part of our experiments, we change our approach by feeding a set of chess puzzles. Because it's only a puzzle, they don't need to remember previous board interactions. They can just learn the current position and then make their move. So it eliminated the variabilities that we demonstrated in the first part of the experiment. In this experiment, we asked the models to find the solution to a set of chess puzzles. And the first set of trials, we asked the model in multiple choice format, meaning that we present the search tree in front of the models so that they don't have to consider only a few options. They are able to consider more options that can help to facilitate their line of thinking. And then we ask for the best move. And then in the second trial, we asked the model to perform in the repeated prompting strategy. So if the model outputted the wrong response, we tell it that it got the wrong response and ask it for another answer. So we offer more tries to the model, attempting to allow them to consider more options other than the wrong option. Of course, we have a set of control variables, control group in zero-shot prompting, meaning that we don't give any additional information and just straight up ask the model for the best move. And the result of the repeated prompting strategy is as follows. The reference groups of zero-shot prompting got an accuracy of 19.8%. And if we offer two attempts to the model, then the accuracy increased to 29.6%. And if we offer 3 tries, then the accuracy increased to 33.4%. So in accordance with the data, there's a clear correlation between more attempts and better accuracy. However, one possible deficiency of this experiment is that it performed better simply because it got multiple choice, not necessarily because it considered more options. And the last part of the experiment, along with the multiple choice questions, the results from multiple choice questions is a prompting strategy. I figure it would be best to collect all the data and present them in a complete graph. So I include a multiple choice question in this experiment, in the conclusion of this experiment as well. So as I explained in the previous section on background studies, there have been many attempts to increase the model's capabilities by employing different prompting strategies. In this experiment, I use zero-shot prompting, the default, and then I also have alternative prompting strategies, the few shots prompting strategy. I specifically use one-shot and two-shot prompting, and also the chain of thought. The methodology is similar to the last experiment. I just asked the model to give answers to the chess puzzles using different prompting strategies. The results of the experiments are as follows. As you can see, in multiple choice questions, the model performed really well. The accuracies are all close to 50%. And in one shot, two shots, chain of thought, there have been relatively little increase in accuracy. However, one shot and two shots still demonstrated some progress. And based on the above data, I also did a graph. As you can see, multiple choice questions, they perform significantly better than other prompting strategies. So a conclusion I got from the data is that as the prompting complexity increases, the model is able to think in a more guided way, and thus their accuracy will increase. So if we architect our prompting strategies based on our specific needs, then we can improve the ability of models to perform well significantly. One interesting conclusion that I draw from the table above is that because I divided the puzzles into 3 sets, easy, intermediate, and hard, in multiple choice questions, instead of performing the best in the easy set of puzzles, the model performs the best in intermediate set of puzzles, meaning that there's more to the models potentially think in a different way than us humans do, and they don't necessarily perform the best in the set of puzzles that us humans consider easy necessarily. However, in one-shot, two-shot, chain of thought, and the reference groups, they do perform in accordance with our human evaluation of the puzzle's difficulties. This statistical anomaly may simply be due to our limited number of trials. In all 3 sets of puzzles, we provided 150. So in total, there are 450 trials done for each prompting strategy. If we increase the number of trials, we may be able to eliminate the anomaly in statistics. So as for conclusion and future research for this study, we demonstrated that GPT-4 is somewhat capable in all these 4 games, but it's still facing challenges in board state interpretation. Although it can solve some puzzles, there's still largely a lot of deficiencies in its ability to perform logical reasoning in these puzzles. And we demonstrate that prompting strategies can have potentially significant impacts on models' performance in solving puzzles and by extension, playing board games. As for future research, we can definitely include more games, more models, more prompting strategies, and more trials. As of right now, every day the model is still improving its capability. And I did the experiment throughout the last year, and if we look at the models in the next few years and redo an experiment on these models, potentially their performance in these board games and puzzles can improve significantly. Thank you.